Hello and welcome to today's webinar, Navigating the Regulatory Challenges of Urban Air Mobility, brought to you by GPS World Magazine and our sponsor of this event, Safran. I'm Brian Davis from North Coast Media, the Senior Marketing and Digital Manager for GPS World, and I will be your event manager for today's presentation. At this time, I'd like to get you comfortable with your console and the ways you can participate during today's presentation. Please notice the Q&A panel on the right corner of your console. If you have a question, please type into the text box and then click Submit to place your question into the queue. You may also use the hashtag GPS World Webinar on Twitter to submit questions during today's webinar or to enter into discussions with other attendees. We encourage you to ask and enter any questions you may have for our speakers during the presentation. We will address these questions at the end of the presentation during our Q&A portion. Questions submitted during registration have already gone to our speakers and may be covered during the presentation. If you experience technical difficulties during today's event, you may use the same Q&A panel on your screen to submit your issue, and my technical support specialist, Danielle, or I will personally assist you. Finally, you may learn more about today's speakers by viewing their photo, bio, and contact information in the panel located on the right side of your console. Now I'd like to introduce our speakers for today. Today we will be hearing from Joseph Bogosian. Joe has more than 30 years of aerospace and defense and government industry experience. For 17 years, he has been leading teams in navigation and timing at Safran Trusted 4D. He is also focused on electrical, optical products and sensor systems and implementing critical international initiatives at Safran HQ. Currently, he now leads Safran USA as president and CEO. Joe is also an FAA Assistant Administrator for International Aviation. Second, we will be hearing from David Dunning. David is the Director of Global Innovation and Policy at Gamma. And David is an industry expert on advanced air mobility and regulatory compliance. Prior to joining Gamma, he served as an AAM program manager with the Federal Aviation Administration and is also a U.S. Air Force veteran. Our third speaker today will be Chris Bauer. Chris is the president and CEO of Hughes Aerospace Corporation, one of the largest globally credentialed air navigation service providers and the industry co-chairman for the U.S. Helicopter Safety Team. Chris has more than 40 years of diverse contributions to aviation. Our final speaker is John Fisher. John is the vice president of advanced R&D at Safran Trusted 4D. For more than 20 years, John has been part of Aurelia, now called Safran Trusted 4D, where he works with global navigation satellite systems, wireless position navigation and timing, as well as specialized systems for its customers. So at this time, I'd like to turn our presentation over to Joseph. Joe, take it away.
Brian, thank you very much for the introduction, and thanks to all who have joined the webinar. At Safran, we're very proud to be sponsoring this highly critical topic. Very timely, and to start off, I thought perhaps with a bit of a humorous note. Last year, George Jetson was born. He's about a year old now, and pretty soon he's going to be flying around the skies, and we better be ready. And our systems have to be ready. So if everything your speakers are going to talk about today doesn't convince you, maybe this would. So at this point, let me turn it over to David to kick us off with our first topic.
Perfect. Thank you, Joe, and thank you to the audience for joining us today. My name is David Dunning, and I am the Director of Global Innovation and Policy at the General Aviation Manufacturers Association, or GAMA. GAMA represents over 140 of the world's leading aircraft manufacturers and aviation service providers. Our Electric Innovation and Propulsion Committee, or EPIC as we call it, is made up of the foremost advanced air mobility companies in the industry today. So in this piece of the webinar, as Joe touched on, we'll explore the current state of advanced air mobility, AAM, with a particular focus on electric vertical takeoff and landing, or eVTOL aircraft, and some of the challenges faced by eVTOL aircraft in the urban environments. We'll cover recent advancements, key players, regulatory developments, and then lead into the next piece of the discussion about enabling urban operations specifically. The first thing I'd like to do is put a little context and frame the discussion today. So defining advanced air mobility. AAM refers to this emerging sector of aviation that is really revolutionizing air transportation with new transformational technologies and propulsion systems. At GAMA, we've worked very closely with our membership to develop a description or definition for AAM that provides the necessary boundaries around the concepts that we're including in this conversation today. So for all intents and purposes, when we say AAM, we're referring to a collection of new transformational technologies applied to the air transportation of people and cargo. AAM aircraft encompass increasingly automated, type certificated aircraft intended to operate in the same environments as existing rotorcraft and airplanes, utilizing air traffic services in the airspace above 400 feet AGL. AAM operations will be integrated into the national airspace system and include pilot on board, remotely piloted, or autonomous aircraft. And noting that many of these new aircraft, several of them combine vertical takeoff and landing capabilities with electric propulsion. Advancements in aviation technology. What's gotten us here today? Significant progress has been made in aviation technology by advances in electric propulsion, battery technology, new innovative designs, and additive manufacturing. eVTOL aircraft represent one of the leading designs in this space and really represent some of the future of certain urban operations. These eVTOL aircraft are designed to be quiet and capable of transporting passengers and cargo. And the potential benefits of eVTOL include reduced congestion, improved efficiencies, lower emissions, and increased connectivity. Some of the key players in the eVTOL industry today, numerous companies ranging from startups to established aerospace manufacturers are very actively engaged in the eVTOL industry. Some of these key players include Joby Aviation, Archer Aviation, Lilium, Beta, Volocopter, Air EV, Overair, eTextron, Wisk, Eve, Supernal, Vertical, Eviation, and Airbus. And I highlight those just to really emphasize the broad spectrum of new entrants that we have here in the space, combined with traditional OEMs. Let's talk a little bit about use cases. The initial use cases for eVTOL aircraft are expected to be cargo and passenger carrying operations in the suburban periphery, or what we're calling regional air mobility. The next advancement in operations is the focus on urban air mobility, or UAM, which offers an alternative transportation solution for congested cities. These aircraft can provide rapid transportation for passengers, cargoes, or critical medical supplies. This will help to reduce ground traffic and the travel time between these urban centers and the airports or their destinations. Additionally, eVTOLs again have potential applications in logistics, emergency medical services, and search and rescue operations. Right now, the FAA, Federal Aviation Administration, EASA, and other civil aviation authorities have initiated efforts to establish regulatory frameworks for eVTOL operations. The challenge here really lies in integrating eVTOL aircraft into existing regulatory frameworks designed primarily for traditional aircraft. So right now, some key considerations include air traffic management, aircraft certification processes, pilot licensing, infrastructure requirements, noise regulations, and environmental considerations. Included on this slide here is a summary of the major milestones achieved so far in the early formulation of these rules by the FAA and EASA. And as you can see, it's a pretty balanced approach and progress made so far with respect to both sides of the Atlantic. Challenges and opportunities. The eVTOL industry holds immense potential, yet several challenges still need to be addressed to really maximize the utility of these aircraft. These include battery technology. High energy density batteries are going to be crucial for extending the range and flight duration of eVTOL aircraft. Infrastructure, the establishment of vertiports and charging infrastructure will be essential for the successful integration of eVTOLs into the national airspace system. And then aircraft certification, meeting the safety and regulatory requirements is a critical milestone for VTOL manufacturers. And lastly, what I'll touch on here today is integrating into the urban environment. Urban air mobility traffic. So as the number of eVTOL aircraft increases, airspace management becomes very critical. Coordinating multiple low altitude flights in urban areas will require a robust air traffic management system that's capable of handling high density traffic safely and efficiently. Urban air traffic management systems aim to manage the integration of crewed and uncrewed aircraft or remotely piloted aircraft, including eVTOL, small UAS, and traditional aircraft within the urban environment. So collaborative efforts are underway to develop standards, protocols, and technologies to ensure seamless and safe operations. I do like to emphasize the note here that early eVTOL operations will be similar to current operations occurring in the national airspace. And what I mean by that is that the initial communication, navigation, and surveillance equipage will be similar to what we are familiar with today and conform to the existing air traffic control construct. So this is a great opportunity to segue into the next portion of the webinar, which dives deeper into the technical aspects of air traffic management within the urban landscape. And with that, I'll pass it back to Joe or Chris.
Thanks, Dave. Really appreciate your taking that first agenda item with current state of the advanced air mobility industry. And like we mentioned, Chris Bauer has joined us from Hughes Aerospace to touch on the second area of focus for our webinar today, which is eVTOL aircraft. So, Chris?
Thank you, Joe. Thank you, David, for the introduction. So while the vehicles themselves get you where you're going, at Hughes, we're focused on how to get there. So operating in an urban environment, particularly like in a Core 30 airport and metroplex, your vehicle is going to encounter a lot of obstructions. And what we have to do is map all of those out. So when we look at a vertiport, a heliport, or a multi-use port, we could call it a multi-port, we go in and we survey that area and we look for what the terrain and obstacles look like. We can capture this data and digitally render it, and then draw out the surfaces, the invisible surfaces, vertically and laterally, that the urban air mobility vehicle is going to navigate. We do this in a way where we look for an ingress and egress. There could be multiple paths to do so. So just to familiarize you with a little bit of the terminology of what we would talk about, is the core of this is performance-based navigation, or PBN. One of the tenets of performance-based navigation is required navigation performance. So what we're saying there is the way we're going to navigate is to use telemetry from satellites and create a containment both laterally and vertically that the vehicle can navigate this path in 3 dimensions from a vertiport to another vertiport, as well as en route. Today we use GPS, which has about a 10-meter accuracy. If you can augment the GPS and create a differential GPS solution, we can get down to sub-meter accuracy, which is what we would require for navigating around areas, around buildings, terrain, or overlapping airspace where we have different vehicles that are also navigating. Vertical navigation is very important because we have to mitigate towers, buildings, trees, fences, wires safely to get you in and out of wherever you want to land and where you want to depart from. So Hughes goes in, we survey the area, both in the vertiport, en route, and also offsite obstacles. And we update the FAA's database with those. Then we can certify the heliport for day-night all-weather operations and make sure that the surfaces are clear and which are the best ways to ingress and egress. This is an example of something we did at the Dallas vertiport in preparation for Heli Expo. So if you look at this graphic from the FAA, you can see that there's a UAM corridor. On the surface, you've got different vehicles that are operating. You've got this corridor where urban air mobility resides, and then above it, larger aircraft that are also navigating. So our focus is survey and data collection to better understand what the safe airspace looks like, then work with air traffic to engineer the airspace to have access at different points laterally and vertically to separate ourselves from the other traffic. We design the procedure, we flight check the procedure, we look at the environmental impacts, and we try to design the procedure to overfly or not overfly an area that is noise sensitive or not noise sensitive to optimize it. All of this gets digitized into a database, and the charting is also digital. It goes for federal publication, and then after that, we maintain the procedure so it's always safe to use. So an example here, the FAA provides us with this graphic of low altitude airways. Today at Hughes, we're able to create these low altitude airways as ZK routes. So the ZK route allows the aircraft to navigate within an RNP, what we talked about earlier, required navigation performance of 0.3 of a mile or 0.3. We know that the law of RNP is that an aircraft will be 95% probability it stays within 2 times the designated RNP value. So what we're saying is on this ZK route, we can navigate within 95% probability within 0.6 of a mile. What's interesting about that is prior to the ZK route, if you were to develop an airway, you would need 8 miles of airspace, which is significant. With the ZK route, we can thread the needle in terms of avoiding obstacles, keeping the aircraft closer to the ground, perhaps out of icing or weather conditions, as well as overlapping airspace with other users that allow us to operate autonomously. We can then take the graphics that we designed from charts for approaches and departures and overlay them in a digital ecosystem, along with weather cameras, and other artifacts that will help either a piloted vehicle operate safely, or perhaps many remote vehicles that are operated, that this data could be present. The graphic on the left is an example of an advanced RNP approach. So advanced RNP is essentially using differential GPS, which could be space-based like WAAS, or it could be ground-based, where you're providing that differential correction to get sub-meter accuracy. And instead of being linear, the advanced RNP is trajectory-based. So if you look, you'll see that there's curves in the approach, and we can have curves in the departure. That allows us to stay away from noise-sensitive areas. It allows us to avoid obstacles and have better minima on the approach. So what are these challenges that we're encountering? Well, nonlinear requires us to think and operate different in a trajectory-based ecosystem and have these different paths. So we're not flying in a straight line. We're starting our procedure perhaps a beam or behind or from just different angles. The containment, differential GPS is necessary to support the required navigation performance required of obstacle mitigation, noise mitigation, etc. Mask angle challenges. Well, you could have those with terrain, But in an urban environment, it's almost like having mountains in front of you. So depending on the altitude of the vehicle, the buildings themselves become challenges in blocking different signals, which can interfere with the aircraft. And that can cause a loss of signal. So how do we compensate for that? And then drift rate is how long the vehicle can continue with the same level of accuracy, that fidelity, for a period of time until the signal is regained. And that's done often with using an inertial system. And a really good inertial system can allow the vehicle to operate for periods of time with the same fidelity until signals are regained and recaptured. Also, the environmental impact. Obviously, if you're going to have a lot of vehicles operating in a closed environment, you want to design procedures that will minimize the impact of these vehicles to the community. So those are some of the challenges. I'd like to give it back over to you. Thanks, Bob.
Great, thank you very much, Chris. Really appreciate that. I think that's a great segue. We'll just keep the narrative going here into how do we enable our urban air operations. And to discuss that topic, we have John Fisher from my company, Safran's trusted 4D division. Thanks, John.
Thank you, Joe. So let's see, let's go on to the next slide here. And we'll talk about the, as Chris had mentioned about the GPS or GNSS signal, the fact that I always say it's great until it isn't. You know, as he mentioned, the fact that it's accurate, especially with WAAS, SBAS, augmentation differential, GPS, GNSS systems that gets you the accuracy. But as we know, we need not only accuracy, we need reliability, we need that availability, high availability rates, and we also need integrity. So we talk about the two weaknesses of GNSS. One, the fact that it's such a weak signal. It's and this goes for all the constellations, GPS, Galileo, all of them. Their satellites are all operating 20,000 kilometers above the Earth. By the time the signal gets to the Earth, it's very weak, and hence, since it's a weak signal, it's easy to be jammed, either from bad guys intentionally or even unintentionally, and or you know, can be masked. There's you get into urban canyons, you get into places where there's terrain masking. It can really weaken the signal. The other thing is that the signal we use, at least in civilian aviation, military has their own encrypted closed system, but the ones that we use in civilian life is an open system. Again, all of them are open systems, and so since they're open, it's great news that we can use it for free. But the bad news is a bad guy can spoof it, and so. And this comes to then the other factor besides reliability. You also need integrity. You think you have a signal, you think you're navigating. Well, can you believe it? Are you being spoofed or not? And so these are the issues with that. So, but there's things we can do about it. And I think the other gentlemen have already covered this, the importance of safety. In this, and especially as we start moving to the unmanned, or I guess uncrewed version of aircraft, the fact that an argument can be made that maybe the reliability and integrity of your navigation system has to be even better than it was now that we don't have a human pilot in the loop. And there's everything about, you know, the safety of the vehicle itself, but also ground safety, other flight corridors. Chris explained a lot about what they're doing in the U.S. about tailoring and mapping good corridors. In Europe, they're doing a U-space concept, so maybe not quite the same, but similar, analogous thing to make sure that we can make these improvements to safety. But so you said you can't depend on just GNSS. It's great when you have it, but there are other things you could do, multi-sensors. So let me go on to the next slide here that shows that, and this was mentioned before, if you start with an inertial navigation system, all right, this is where you have accelerometers and gyroscopes, and without any external reference, you are knowing you can only navigate with, and so you can't be jammed, you can't be spoofed. But then you add to that the GNSS signal, improve your accuracy, reduce your drift rates. You can add other sensors. You know, you have maybe altimeter readings. There's even now, I think in the future, we're going to see what we call signals of opportunity. We're able to have the processing power to what we call sensor fusion, to take navigation aids, inertial navigation, and even other radio signals, maybe communication signals that were not designed for navigation, but that can be used for that. And they all get into, and we call that sensor fusion, and going into then a navigation unit that can really give you that high reliability, high integrity methods that you need. And so I'm going to show here something is a nice data chart that DARPA had created, and to kind of explain inertial technology. And if you're new to what an inertial navigation system is, I'll start out to say that you actually have a inertial measurement unit, a low grade device in your phones. That's how your phone knows which way is up, and you can shake it, and as you move along, it knows how many steps you take and stuff. So there's accelerometers and gyroscopes. They're very low quality, low cost, very low. In fact, on this graph, we have a metric we call SWaP-C, size, weight, and power and cost. And so low cost, low power, small size is on the left hand of the axis. And as we move to the right, things get more expensive, get bigger. So we start out at that lower left-hand corner with what I'll call that consumer grade IMU, and the y-axis being its accuracy, or what's the how much time, how much drift rate. It's a measure of drift rate. How much time does it take before your error grows to 10 meters, to now unaided GPS kind of values. And so as you see, if we're at these low end ones, even the automotive ones, it'll happen very quickly. If we get into what we call tactical ones, which are a bit more expensive, a bit bigger, still not quite at the time, at the performance we need to do this air mobility function. We have to get up into what we call navigation grade inertial systems. And of the navigation grade, and I've kind of highlighted in red here, what we call the HRG type, the hemispherical resonating gyro. And there's been in recent years, real breakthroughs in that navigation grade technology. We've had these in the past, but they've always, as you know, you see here, they've been out on that out on the x-axis of being expensive and large and not really suitable for, especially for like a VTOL or an eVTOL kind of application. But the breakthroughs of recent years have made that much more affordable, and where we can get now with a standalone HRG system of getting the required navigation performance of 30 minutes or greater, which really covers a lot of the urban air mobility missions and so now you have that again, reminder that an inertial system is impervious to jamming and spoofing. You still use those other sensors to improve on it. You always want to have diversity for reliability reasons, for no single point failures. But we do have something which now can do that and give you the needed integrity, reliability, availability, and accuracy, everything you need. And in fact, I'll show you here just as an example of one of the products we make, the Skynaut. Give you some of the specifications there, but this is it's best in class of navigation grade devices. Inertial, it has inertial measurement. It has a GNSS receiver. It does the sensor fusion function. Lowest life cycle cost, best in class for swap for size, weight, and power. So really meeting those new requirements for lightweight, affordable for these missions. As I said, it has those sensor fusion characteristics, and but it does have GNSS as well. So you get the added when GNSS is there, it will enhance the performance. You can do even better, and not just a simple GNSS receiver, but with algorithms internally that do interference detection and mitigation. So there are things you can do, and this is what really improves integrity, is knowing that, okay, knowing that you may be being spoofed, or knowing that you may be having jamming and getting a reduction in your signal. So that's just one of many. I won't go into the details here, but we have several HRG type products, and you could probably find out more on our website. I guess so we have more than 15 million combined hours of operation. We do land, sea, and air, and space systems. So that technology, as new as it is, it's also mature enough to be depended on. So with that, I think I will turn it over to you, Joe.
John, thank you very much. As Brian mentioned at the outset, I came to the Safran Group in 2007 from the FAA, and it's actually great to be coming full circle here and coming back into issues which very much implicate and rely on the involvement of FAA and EASA in coming up with the systems that we need. The speakers went through, and I just want to highlight a few of the points in that we definitely have a significant expansion of activities. As Dave mentioned, we have more technology, more airframers. We have crewed and uncrewed solutions that are coming into play. And so suffice it to say, industry is here. Dave talked about the key players. Chris talked about how they support performance-based navigation at Hughes. John talked about how at Safran Trusted 4D, the technology is here for more assured, more precise navigation and timing. Next year at the Paris Olympics, there's talk of some demonstrations, either crewed or uncrewed, in Paris to demonstrate urban air mobility. And so all that to say that as Dave mentioned, the challenges and the opportunities are right here. They're very present. We have to address the battery technology issues. We have to address the infrastructure issues. We have to address the certification issues. And when it comes to certification, we'd love to see all the progress at FAA and EASA. I think one point there would be that because these will be pretty much local, regional, national operations, harmonization would be a nice to have. It'd be great, but it's not a must have. So we really just would love to see the progress in both US and Europe. As Chris was going through the vertiports and the air corridors, it's really interesting in that there's a lot of familiar topics, but it's going to be a very different world. If the skies aren't already crowded or getting greater use, they're going to get even more use coming into the future. And so managing performance-based navigation, getting us up to speed. We have to think and operate differently tomorrow than we do today. If today you rent a car and the GPS goes off, that's annoying. Well, if the GPS is not assured in the future, that means the stakes are much higher, and there's safety and lives at stake. And so we have to take care of the weaknesses in GNSS. And I'd like to show a slide, and credit to Karen Van Dyke from DOT. She's director of the Office of PNT Spectrum Management. She presented these points a couple of weeks ago at the PNT Advisory Board meeting. And what she highlighted were that with Space Policy Directive 7 that concerns PNT, DOT is focusing on these high-level requirements. They've identified these high-level requirements. What I'd like to do is sort of open it up to our panelists as to lead off the Q&A section here, and say, Dave, Chris, John, which of these requirements do you think are most critical to urban air mobility, and maybe prioritize them in criticality and time and importance?
So I guess I'll go with the first one, if that's all right. The fact that federal interagency of implementing IDM, what we call interference detection mitigation capability, we said that's an important thing. At the very least, you need to know that there is some interference in the area. And so that kind, and the Department of Transportation is setting up those kinds of, almost like, I think we kind of call it like a weather reporting thing, right? The FAA will report on, or NOAA reports on weather, so that we know where there's going to be problems. They're looking about doing that same kind of thing for GNSS interference. And Chris, the kind of corridor, you said non-linear trajectory things of where, if I understood you correctly, you can avoid some of those if there's a nasty, stormy area for GNSS. Is that correct?
Yes, absolutely. You're going to need a multiplicity of different trajectory paths to serve the area that you're operating in, because you're going to have vehicles that you're going to have delays. I think some people look at this just from the idea of one vehicle arriving at a vertiport. But if you could imagine, say there's 100 vehicles arriving in an hour, or 50 vehicles arriving and departing in an hour, and one of them for some reason is delayed, the other vehicles have to go someplace else. So you would have to approach and depart the facility on different trajectories, either because of noise, because of weather, or a disabled vehicle. I would jump right into two and say, whatever we're doing has to be multi-agency coordinated, and there has to be buy-in. If you look at I'll call it disappointing rollout of 5G, the number of NOTAMs that went out, the number of impacts to safety and aviation because of just a lack of coordination with 5G. And then as a pilot, you go out and you fly, and all of a sudden the GPS constellation is being taken off the air by the military in some pretty prime real estate where you have no GPS coverage, say, for 250 miles in an area out west. And that's devastating to being able to operate, considering that most of the NAS today is depending on GPS for not just navigation, but ADS-B surveillance and a host of other functionalities. So I would look to almost a czar appointed by the government that can go across different agencies and make sure that everybody's coordinated as to what the nav specs are, the availability of navigation aids, and the stability of them as well.
Thank you, Chris. Thank you, John. And I think at this point, if we could open it up to the Q&A that's been coming in. I think that there's definitely a number of questions that have arrived. Brian, do you want to walk us through some of those?
Yes, thanks, Joe. We're going to jump into some questions. We've had some submitted questions. We also have quite a few coming through the Q&A. We'll start with number one. What will be the recommended best organization of regulation between UAM and an airport administration for the same city?
Brian, I can jump in and field this first. I think while we're still in the very early stages of rule formation, what's really most important is that local, state, regional, tribal regulations don't get too far out ahead of the FAA and EASA with respect to final rules and final advisory circulars and guidance. What we don't want to have happen is that we end up with misaligned rules and regulations, one agency getting out ahead of another at a local level. So patience right now. The FAA is expected to publish a final vertiport advisory circular in 2025. EASA has currently published their proposal for vertiport guidance within their regulatory framework, and ICAO has recently stood up a vertiport design subgroup to address these issues as well.
All right, thanks, David. What are the enhancements needed to the current GPS for use by UAS and emerging modes of transportation?
This is Chris.
Go ahead, Chris.
I could just give a thought on that. Reliability and dependability of the core GPS system. Working on second frequency for WAAS or SBAS, and harmonizing that with Europe and other regulators that are using space-based augmentation. It would be very purposeful, regardless of it's an urban air mobility vehicle or an airliner or general aviation, vertical flight, that we have sub-meter accuracy in the NAS to provide the navigation. And also a lack of interference from other transmissions, such as 5G, that could interfere with the aircraft's performance. I'd also throw out there, it was mentioned in the webinar about GPS jamming and interference because it's such a low impedance of the signal that we have to get serious about people buying GPS jammers and turning them on and the effect that it could have on aircraft safety. That needs to go away. Thank you.
Yes, and I couldn't agree with you more. It really becomes an enforcement issue, and I see in the Q&A not a question but a statement by Mitch Narens, who's quite knowledgeable in this field as a former FAA systems engineer, and he says the fact that most of the national airspace is dependent on GPS is a problem and not in accordance with FAA's own performance-based navigation strategy. So that's a good point too, and I think it goes into the thing. Yes, there's things we can do to enhance it, the multi-frequency. In fact, you get a lot of benefits with multi-frequency. As Chris mentioned, you get not only it becomes harder to jam, you got to jam more frequencies if you're going to do that, so you get an extra level of reliability. You get multi-frequency also gives you improved accuracy and that. But to the larger point, you can't just depend on GPS, GNSS. So yes, the enhancements are good, the detection methods are good, but that alone can't do it. You really do need to have inertial navigation as well.
Excellent. Thank you, David. Let's see. I got another question from the chat. How should UAM be supported by the integration of both RF and non-RF sensors, especially as a means to support integrity? They gave some examples: compass, barometer, altimeter, attitude understanding, terrain features, etc.
Yes. Yes, that's what we refer to as sensor fusion. So yes, you know, compass, you don't quite get the accuracy, but if you're again the inertial technology that we described of this HRG is also accurate enough to give you what we call gyroscopic compassing, or some people call north-seeking compassing. So much more accurate than magnetic compassing. Again, the kind of accuracies that we need is more important. Altimeter, radar altimeters give you very good accuracy in the Z direction. And now, of course, as we start adding, you know, as Hughes is doing with their like digital mapping, and then also with cameras, with lidars, with forward-looking radar, forward-looking IR systems, that those can be sensors as well that go in there. So we have the processing power to do that level of lots of complex processing, and so I think we'll see that in the future, and we call that all under the subject, under the, we'll say, hashtag of sensor fusion.
Excellent. Thanks, David. Another question, what might ground equipment for IFR operations at a vertiport look like?
I'll take that one if you like. Actually, there wouldn't be any ground equipment. That's the beauty of this. It's all space-based. So assuming your heliport or vertiport is suitable for VFR operations, you have markings, you have a windsock, you have lighting if you anticipate night operations. That's really all the equipment you would have there, plus whatever equipment you would need to comply with local regulations such as fire equipment, fire suppression, fencing and stuff to, say, separate an area from the passengers. But in terms of the navigation piece, it's all space-based. So what we would design and implement would be a space-based, augmented, vertically guided navigation procedure, basically an LPV, to the vertiport, along with a departure that would allow the aircraft to operate in all weather conditions. And today, as of where we stand right now, we can get down to 3/4 of a statute mile and 250 feet height above heliport surface.
We have another question from Joseph. Are there navigation grade INS systems light enough for small, medium drone usage?
Yes, I'll take that one, and I think the answer is unequivocally yes. I think that's where, as I said, the HRG technology, recent years of where we've had this breakthrough of now navigation grade, but light enough. I think, as I showed, the one, and this is already a mature product, our Skynaut, of which is 3 liters high. I think it's only something like 5 kilograms. Yes, it's light enough and cost effective enough too. I would say you can't put $1 million navigation system inside a less than $1 million aircraft kind of thing. So, both size, weight, power, and cost, it is now affordable.
Thanks, John. Question from David. Will computer vision of landmarks be part of sensor fusion?
I guess as a technologist, I'll give that answer that yes, it's possible, but maybe it'd be interesting to hear from the more operational folks, David and Chris. Is that, from an operational point of view, do you see that as coming in the future?
This is Chris. It has potential, but there's no criteria today to support it in terms of using it. You know, if you operate drones as we do when we survey, The drones will take an image of where it took off from. So when it returns, it uses a confluence of GPS navigation as well as photo recognition to see if that's where it needs to be. But it's still in its very early stages. Even the use of FLIR and biz jets for night operations has proliferated, but the FAA doesn't give any additional credit for that or synthetic vision. So I would put this in that same group of nice to haves, but there's nothing that's going to give you any regulatory relief in the near term for it.
Maybe it's still in George Jetson's thing, not quite here yet today. Okay.
Yeah. Another question from Mitch. What credit is given the pilot in ensuring safety, and how will that metric be applied as a requirement for the design of an autonomous solutions? In what situations?
I'm focused more on the unmanned, uncrewed one. So in general, that's where we're looking towards about becoming not having to depend on a pilot. But again, I'll defer to you more operational folks that know more about it than I.
All
This
right,
is
and we're
Chris.
gonna.
I could speak as a pilot, which I don't know that would answer Mitch's question. I mean, obviously the technology is moving more and more towards not just piloted operations, but let's say in the medium, like single piloted operations, where you have one pilot that's operating a vehicle that could be IFR, as a lot of HEMS operators do today in helicopters, where you have a single pilot flying IFR on NVGs. And you can use this technology to reduce the workload. As far as eliminating the pilot with that technology, I'm not the right person to answer the question, but I think there's a lot of, I guess, ground that has to be covered in terms of reliability and what we spoke about earlier, spoofing, interference, jamming, and what, if that occurs, how does the vehicle recover from that if it's not piloted?
All right, I'm going to ask two more questions. The next one being from Dan. Is there a need for industry guidance for use of non-traditional navigation sensors for safety critical operations? An example is a new RTCA special committee.
Very, very generally. Go ahead, John.
No, I was going to say, in fact, I would say yes, and I'd like to. I was going to invite you, David, to answer that because you have a better understanding of the standards committee stuff.
Sure, and leaning on your technical expertise, I'll say yes, agree, and really foot stomping that we're still in the very early stages of understanding, what the evolution is going to be with respect to timeline here. So we are still in the beginning stages of advanced air mobility, and just to provide a little color, we anticipate piloted, pilot onboard eVTOL operations to begin in 2025, and then pivoting to the first remotely piloted operations occurring 3 to 5 years afterwards. So let's call that loosely 2030. And then further into the future, and we have not put boundaries around this, I don't think there's very clear understanding yet of when exactly autonomous operations will begin. But let's put that in the 10 to 15 year plus bucket for this conversation.
Thanks, Dave. I'm going to wrap it up with one final question to wrap up today's event. What, if any, regulation are we seeing regarding mandating GNSS resilience to jamming attacks for AAM?
Okay, so I'm going to give the technologist answer to that one. Is that you can make all the regulations you want in the world. It's not going to change the fact that weak signals from those satellites are easy to jam. And so there's going to be bad guys. There's going to be breaking the laws. We have to do, as we said before, much more about enforcement and making it a serious crime to do this. But again, we're talking about safety of life, air safety. You can't leave things to chance. So I don't think, again, short of more enforcement, I don't think you can depend solely on regulation to fix the GNSS vulnerability problem. Now, I guess there are things you can do as far as the vulnerabilities, like in urban canyons and in GNSS, the fact that less availability in canyons and things that we can do of those more controlled situations. Yeah, there's I think there's things we can do there, but I wouldn't rely on regulations any more than just enforce the laws that we have now severely.
Excellent. Thank you, John. I think that's all of our questions for today. Did an excellent job. I'd like to thank our speakers, our presenters, for a great presentation today. I'm going to wrap up this live event. Thank you for attending the Navigating and Regulatory Challenges of Urban Air Mobility, brought to you by GPS World Magazine and our sponsor of the event, Safran. If we were not able to answer your questions during the presentation or the Q&A session today, your questions will be forwarded to the speakers to be addressed at a later date. You can also contact our speakers through their emails on this slide. A recording of this webinar and other upcoming webinars from GPS World will be posted at gpsworld.com/webinars. We'd like to thank you all for attending today, and we hope you will join us again for another GPS World webinar. Thank you.